universe, estimated to be 13.82 billion years old. With the diameter so far, the only thing we could tell is at least 93 billion light years. I mean, considering all the voids and filaments that are made up with superclusters, compromising in galaxy clusters that are basically made up of galaxy groups formed by individual galaxies, which then themselves are made up of billions of stars, planets, and objects, that's a lot to take in. Despite the astronomical challenges facing this field of study, the advancements in science, technology, and especially data mining, has let our understanding of the entire universe go by leaps and bounds. It's thanks to advancements in CPUs, global and wireless interactivity, and the development of highly sensitive instruments that we can now strap onto telescopes. It's because of all those things that we can now collect, sort, and analyze data from multiple sources all around the globe with just a few lines of code. Just take a look at Michael Chang, an associate from the Google's data art team. Using information they collected from 3 surveys only, they managed to create an interactive 3D model of our stellar neighborhood, comprised of 100,000 stars that you can just access with your own browser. It really gives you a grand sense of scale, just like how much is out there, and just how little we actually know. Although the simulation is indeed impressive, none of it would have been possible without someone first querying through multiple terabytes of information, obtained through numerous data sources managed by multiple research labs and observatories, as well as private companies too. So you see, my goal here, other than to cultivate my editing skills, as well as probably work my directing and acting at this point, is to basically teach you of a tool that offers a uniform way of searching and storing the select information you would want to use in perhaps your own model or for your own research. So, as I said, there are numerous surveys out there that sort information collected from all the different satellites and observatories around the world. But you see, these surveys don't always match the same set of data. See, it really depends on what that institution is actually trying to research. See, some surveys focus more on the actual development of our Milky Way galaxy, while others are basically more so interested in interplanetary exploration. So, depending on which site you actually access, you could be collecting information that may not even be relevant to you. Now, most of the databases you'll pull information from stores its data in the form of FITS files. And what FITS files are flexible image transport systems. So they're not basically just images you're looking at. It's basically a file that not only stores the image, but all the metadata accompanied with that image. You see, these files commonly come under a header, which allows you to traverse the large amounts of information with a single file. So a FITS file for a single star could also store its ascension, declination, as well as its magnitude, color spectrum, and its calculated distance from Earth. But to ease the burden on both of us, I found a simple means of accessing FITS files with Python. And to further make it less stressful, I'll be showcasing how to run these programs on a Linux virtual machine with a MapReduce v1 installed. So assuming you haven't thrown out your computer from the 4th lecture, I think you'll be okay. Now there are 2 libraries I used. One is called Astronomy, which is a Python library filled with functions used in astrophysics, while the other is AstroQuery, a library that will allow you to query through databases dedicated to observational astronomy. You see, AstroQuery was designed to utilize Astrobay's mathematical functions in order to create sophisticated queries that will let you search through different measurements of data. But in order for Astronomy to function properly, it requires the use of several other libraries that are typically used by engineers and data scientists. NumPy and Matplot library are just 2 libraries that Astronomy uses to its advantage. But let's get started. In the comment section, you'll find I provided a link to a text file that should give you the necessary commands to install all the libraries you need via the simple terminal commands. If you do not have pip installed on your machine, simply download this file here. And after that, just type in python.getpip.py under whichever directory you downloaded the file to. This will install the package manager and allow for simple one-line installations of Python libraries. From there, you'll want to start installing all of the libraries. So that includes NumPy, IPython, Matplot library, beautiful job. I found that relying on pip, a package manager for Python, is the simplest way of getting necessary libraries installed. Typically, the standard line is read as pip install and then the library. So why go through all this minimal effort? Remember those FITS files I mentioned earlier alongside the poor screenshot? How they're all stored in different surveys and databases? Well, AstroQuery was designed to provide a common API between all of them. So let's start with loading a module to access and query the Sloan Digital Skies Survey database. Once we enter our Python environment, all we have to do is astroquery.sdss import SDSS. Very simple. And that's literally the same method you would utilize any other survey. Say instead you want to access the Simbad survey. You would use the same exact setup in Python terminal line. So, from astroquery.simbad import Simbad. Ta-da! Very simple. So, not only do we have access to the Simbad survey at this moment, we also have access to the Sloan Sky survey. And AstroQuery gives you about 28 of these databases. See, you can import multiple modules for different libraries. Thus, your program can pull and compare readings for the same set of coordinates from multiple sources. This can allow you to pull in different information for the same set of objects. But now that we have access to the SDSS survey under our variable SDSS, next we want to pull a list of objects from a set of coordinates. This requires us to utilize our second library, Astroby. You see, Astroby is a package designed to perform astrophysics. The return result from our calculations are then used to sort through the dataset accessed by AstroQuery. So before we can begin, we'll need to create a set of celestial coordinates. This requires a bit of explanation. You see, to generate a set of celestial coordinates, we need to utilize the SkyCoord class of Astroby. You see, SkyCoord allows for a variety of inputs, but the most common are typically the right ascension, the declination, a unit of measurement, and the celestial reference frame. More often than not, though, your unit of measurement will be degrees. You can also use hour angles, even parsecs as your unit of measurement as well, but for simplicity, let's just stick with the degrees. And now, if you're great at Jeopardy, then you know what the other three inputs actually refer to. Otherwise, if you were like me, you had to Google it. You see, the right ascension and declination are used to specify the direction of a point on a celestial sphere. Now, what's a celestial sphere? I had to Google that too. Think of it as an imaginary sphere that encases an object, or in this example, the Earth. If you think of the observable sky as the inner surface of our imaginary sphere, then you can pretend that each visible object in the sky is a specific plot on a map. Although your viewpoint of that object shifts, the object itself stays relatively in the same location. We use the right ascension and declination to describe where a celestial object appears on the inner surface of this imaginary sphere. Of course, we keep that in relation to the intersection of the celestial equator and the visible path of the sun, also known as the ecliptic. But as for the celestial reference frame, that actually refers to the system used to identify celestial objects' location in a three-dimensional space. Frame references differ by what we consider the origin of our mapping. For example, the International Celestial Reference System, or the ICRS for short, looks at the barycenter of the solar system as the origin, while the Galactic Coordinates System uses our sun as the origin. The ICRS was adopted in 1998, and is currently the default value for this method. It's quite a bit to wrap your head around, yeah? When plotting out objects in a 3D space in relation to the ecliptic is kind of a lesson in and of itself. If you had to learn something from that explanation, just plug in two numbers and set the unit of measurement to degrees. That's basically all you need to know to get forward. So, let's create a usable coordinate object, and from there perform a search at that location. To do this, we use the SkyCoord class and our three pieces of information. So, let's make a variable search sky. Why not? And we'll set that to sky coordinates with some random numbers. Some random right ascension and some random declination. Sounds good. And we'll set the units to degrees. Oh, and for those who are familiar with sexagesimal numbers, we can also use those numbers as our input for the right ascension and the declination. Instead of entering them as simply numbers though, we have to enter them as strings. So, I've converted this before offhand, so if we wanted the same ascension and declination in hexagesmal number, this would be, and just so we can show a difference between the two. See? Because if we print our first one, we end up with a right ascension and decimal, basically the same exact as our input. However, if we do one where we use the sexagesimal numbers, we actually end up with the same exact coordinates. So even though we entered our inputs at sexagesimal numbers, they automatically turn back in degrees after our coordinates is set. This class automatically converts our inputs to degrees based on the frame of reference we originally chose. So now let's find an object at this set of coordinates. We can do this simply by using the command query region, which returns all the objects found within our database that are found nearby this set of coordinates. And our results actually are returned to us in the form of a table. The list of objects found returns a few basic headers, such as the right ascension and declination, and the rest of the fields actually correspond to under what conditions the object was photographed. You see, the object ID you see right here is actually a combination of all the photographs data attached into a single 64-bit integer. Now, this information is not really necessary for our exercise, but if you're looking to get involved with the field further, you might want to read up on it. From our results, we have 18 items returned in the form of a table. In any case, perhaps we want to simplify our findings. The query region includes everything within a 2 arcsec radius from the specific location we gave as our coordinates. So if we want to lessen our results, we could shorten the radius of our search. You see, the units module of the Astronomy library allows us to easily convert numbers into different astronomical numbers. So for example, as I said, we currently have 2 arcsecs radius as our default search range. How about instead we change it to 0.1? Of course, if we just put 0.1, it basically just thinks of it as 0.1. This doesn't convert into anything. But if we want to convert this to arcseconds, all we would have to do is take the units module we already imported and just put that automatically converts it for us. And so if we print it out again, we only lost 2 objects. This doesn't seem to do much for us though. So let's attempt one last filter for our query by selecting only items in which we also have spectroscopy measurements, or more specifically which records also store information on the wavelengths of light being emitted from each object. In order to do that, all we have to do is add one more argument to our query region method. Spectra is basically an argument that asks if we want to include the spectroscopy measurements. In order to filter the items that have the spectroscopy measurements, we need to add the spectro argument to our query region call and set that variable to true. And now, once we actually print our results again, we only have one item left. And with our single item, I'm quite actually curious what it is. So let's take a closer look at our results. So, now that we have a desired object discovered at our coordinates, we can download the FITS file associated with it and learn more about it. In order to do so we call on the AstroQuery module SDSS, as that's where our database is, and what we've been searching through. All we do is get images matches equal to our previous object. What this command line does is pull all the FITS files that share the same metadata from our previous query and stores them in an HDU list. Now, an HDU list is a class of objects defined under the Astronomy library. They are very similar to the list you would normally find in Python, but these were specifically designed to be able to read the headers associated with these images. So now if we were to do images.info, we actually get all the information associated with this FITS file. With the info function, we can now see how the FITS file is set up. The first item in the HDU list is the primary object that lists the most amount of information about this FITS file. If we actually see that information over here in the Python environment, all we have to do is use the actual header function as provided by Astronomy. So we call on the first object of our HDU list and just call the header. And as you see, here's all the information that was stored in that FITS file that we downloaded. We can also get a sense of the type of image that was pulled with this FITS file by observing the shape of the data. Getting HDU list data is actually quite easy. All you have to do is type data. Literally. That's all you have to do. But however, if we want the actual shape of this data, then all we have to do is use the command shape. And as you see, it ends up returning 2 dimensions. For example, there are actually cases where your return file will end up showing 3 dimensions, which in that case it's either like a 3D cube or it's supposed to be a simulation. You'll need to flatten or transform the data before performing further calculations on it. But for now, we're just going to stick with simple 2D images. Now an issue is, neither AstroQuery nor Astroby has a function to display the image from our FITS file. Instead, we have to rely on the pyplot from the matplot library. See, matplot library has a function called imshow, which buffers the image data we just viewed, which would be this big array right over here. We can also apply a color map to the image to give it a bit more definition. But of course, before we can do that, we have to actually import the library matplotlib, and more specifically, its pyplot module. And from there, we can now actually display this information. And just for convenience sakes, I'm gonna set the information we captured to an easier variable to read. So, all we have to do is pl.imshow data, and I'm gonna go with a hot color mapping. And our resulting query returns a large black screen with maybe a dot or 2 of red. Well, see, isn't the universe amazing? And just kidding. You see, when we looked at this set of return data, you should have noticed that all of our data points were actually not that far off from each other. If we really want to see the image captured in this file, we're going to have to normalize the data. And this could easily be done again with the imshow function. All we need to do is add a norm parameter to our function call. And typically, we would end up using a log norm. And of course, in order to do that, we need the actual proper method to call it. And in this case, that would be, again, matplot library, .colors, and we import log norm. And so if we want to utilize that function now in our imshow, we would set the norm parameter to log norm. And you see from here, we have a much different scale. And we can actually see a couple of objects. In fact, some of these things, this for example, kind of looks like a galaxy. And this right here kind of looks like a star. Although I honestly can't really tell yet. Although the image is a tiny bit better, perhaps we want to improve it a bit more. You see, we can actually clear out the picture a tiny bit more by limiting the log values. And we end up doing that with the actual log norm function itself. So we could set the minimum to 0.1, and we could set the max to 1. So for every value that ends up being lower than 0.01 will actually be set to 0.01, and for every value higher than 1 will automatically be set to 1. This will help actually balance out the overall image. So our end result shows us a variety of objects. Some which look like stars, and others look like galaxies farther off in the distance. Of course, it will take more calculations to determine the distance and magnitude of these objects, but we would be able to perform these calculations pretty easily using the functions provided by the Astroby library. So you see, this is just the bare minimum of what you could do with these tools. There are ways of creating sky map positions, pointing out the locations of select celestial bodies in relation to your own view of the Earth, making scatter plots comparing stars of different types of magnitudes, or just copying Michael Chang and the rest of his group, and use the right ascension and declinations of the randomly observed stars bearing certain levels of magnitude to create a 3D model. Whatever floats your boat. The possibilities are near endless, and though this tutorial did not showcase anything too crazy, I would at least give you a sense of how many resources you have out there, and just how easily you can use them. Thank you for watching, and please give me a good grade.